Welcome. Let's pick up where we left off in our discussion of extrema of functions of two variables. So we had established what critical points are and how to find them. And so they are a tool to identify maximum and minimum values, much as we did in Calc 1. So let's take a look at FERMAT'S theorem, because just because there's a critical point at a point x naught, y naught does not guarantee that there's an extrema. So FERMAT'S theorem says that if we have a function of two variables that is defined and continuous on an open set containing the point, this would ideally be your critical point, and suppose both the first partial derivatives of f at x in the x direction and in the y direction at that point exist. If f has a local extremum at that point, then that point is a critical point. So if there's a local extrema, then the point is a critical point. Note this theorem does not say if there is a critical point, then there is a local extrema. So please be careful. The converse of this statement is not true. So from single variable calculus, you have a notion of what local extrema, local maximum, local minimums are. But we don't have a saddle point in single variable calculus. So let's go ahead and define what a saddle point is. So given a function, f of x and y, at the point x naught, y naught, f of x naught, y naught, so at the z value that corresponds to x naught, y naught, that is a saddle point if both partial derivatives are equal to 0, but f does not have a local extrema. So here's a picture of a saddle point. We can see roughly a saddle, and so there's a saddle point right here. And you might be wondering, well, how can it happen that both of our first partial derivatives are equal to 0, but there's not a local extrema? So let's look at the partial of f with respect to x. I'm going to draw that trace here in purple. And so what we see happening is we have something that somewhat resembles a parabola. It's not a parabola, but it resembles it. And notice how that saddle point appears to be at the vertex. You could think about the slope of the tangent line being 0 at that point as long as we remained parallel to the x-axis. And now let's consider the direction parallel to the y-axis. So the direction parallel to the y-axis, let's see, we'll do that. Let's try orange. We see something that resembles a parabola opening downward. Now, it's not a parabola, but it resembles it. It helps us think about it. And this is in the direction parallel to the y-axis. And so we can consider, what would the derivative be right here if we're looking strictly in the y direction, and notice that that derivative should be 0 because there's a relative maximum in the y direction there. So that's how you can have both partial derivatives equal to 0 but not have a relative maximum or a local maximum or minimum. So now that we know how to find critical points, as we saw in the first part of this video, we're ready to test those critical points to determine whether there is local extrema at those points. So the second derivative test is the tool that we use. There is no analogous first derivative test in multivariable calculus. So let's take a look at the second derivative test. So first of all, our function has to have first and second order partial derivatives that are continuous at some point on some disk containing the point we're interested in. And notice that we're only looking at critical points for which our first partial derivatives are equal to 0. Next, we define this quantity, this D quantity. It's actually a determinant of a matrix called a Hessian matrix that contains the second partial derivatives of the function. We're not going to approach that this way. We're just going to use this formula, but it is called a D most likely because it is a determinant of a matrix. So notice the structure here, and notice that if this D is positive, so in I and II, if D is positive, then if this second partial derivative with respect to x is positive, we have a local minimum. This second part is very similar to what we do in single variable calculus. And in II, if that second partial derivative with respect to x both times is negative, then we have a local maximum. So I and II are very similar to what we do in single variable calculus. The only additional piece is that we have to ensure that this D, this quantity, is actually positive. If D is negative, then F has a saddle point at that x naught, y naught. And if D is equal to 0, the test is inconclusive, and we'd have to use a different strategy to try to determine whether that critical point was a relative maximum or a relative minimum. So let's go ahead and return to that function we saw earlier, where we found the critical points, -1, 5 halves, and 3, -3 halves. And let's go ahead and determine whether these are local maximums, local minimums, or a saddle point, or maybe we won't be able to tell. And over here on the right is this D formula for our reference in constructing that quantity so that we can determine the presence of extrema. So we had previously found that the partial derivative of f with respect to x was 3x squared plus 6y minus 18, and that the partial derivative of f with respect to y was 6y plus 6x minus 9. Now notice for D we need the second partial derivatives, so let's go ahead and compute those. Now the second partial derivative with respect to x both times of f is going to be 6x from the first term and 0 for the remaining two terms. We also need the partial of f with respect to x first, then y. If I do that, then x first, so I'm looking at this partial derivative, then the derivative with respect to y, I'll have 0 plus 6 plus 0, so this is simply 6. And then I also need f sub yy. So partial derivative of f with respect to y both times. That's going to give me a 6 from the first term, and that's the only term that contains a y, so the other two terms have partial derivatives of 0 when taken with respect to y. So now we have our two critical points, so let's first find D when we use the critical point -1, 5 halves. So that's going to be f sub xx, so 6 times, I pull my x value in, so 6 times -1 times f sub yy. Notice there's no variable there, so I will just write the constant 6, minus f sub xy. Notice again, this one is also a constant, so minus that squared. And what I notice here is I have basically -36 minus 36. That's going to give me a negative number. And I really only need to know whether D is positive or negative. So D is negative. And so if we go back and check when D is negative, we have a saddle point. So the critical point we had used was -1, 5 halves. And so we have a saddle point at -1 and 5 halves. Now if I evaluate my function at -1, 5 halves, I get 41 over 12. So we have a saddle point occurring at the point -1, 5/2, 41/12. Now let's go ahead and do that for our similar thing for our second critical point. So now we're finding D, or the determinant, when x is 3 and y is -3/2. So starting with f sub xx, we're going to have 6 times, and we pull in our x value, which was 3, times f sub yy, we saw that that was a constant, that's 6, minus, and then f sub xy squared. Notice that's also a constant, so we just pull that constant value in and square it. Now, when I look at this, I could certainly run it through my calculator, but all I'm really interested in is this positive or is this negative? So what I notice is I have 3 times 6 squared times 1 times 6 squared, or 3 copies of 36 minus 1 copy of 36. This is going to be a positive value. Now recall that when D is positive, then we also need to know the value of f sub xx. So let's go ahead and find out what f sub xx is at 3, -3/2. And we already really have that here in this first set of brackets. That's 6 times 3, which is a positive value as well. So our D is positive, our f sub xx is positive, so what does that tell us about this critical point? Notice that our D value is positive and our second partial derivative with respect to x both times was positive, so that tells us that at this point there is a local minimum. Now if I evaluate my function f of x and y at 3, -3/2, I have an output of -119/4. So this tells me that we have a local minimum of -119/4 at the point 3, -3/2. So let's take a look at this surface. Here we have a graph of the surface, and we can see how our saddle point and our relative minimum can be captured on this graph. We see a saddle behavior happening over here, and so we found that our saddle point was at -1, 5/2. So -1 is right about here. 5/2 is going to be right about here. So our saddle point corresponds to -1, 5/2, 9/4. We also had a relative minimum, and we can see some kind of minimum behavior occurring right in here. We found that our relative minimum occurred at 3 for x, -3/2 for y, so that's right about there, and that negative minimum value was -119/4. So 3, -3/2, 119/4, and that was negative. I hope you find this helpful.